Good morning all. Today's class is about dental composite part 1. So in which we will see about the material aspect of dental composites in short. So coming on to introduction, composite resin is three-dimensional combination of two or more chemically different materials with a distinct interface between them in combination. The properties are superior to those of individual components. So in 1955, Bunicov he introduced the acid etch technique. In 1956, Bowen formulated bis GMA resin. In 2005, silver composites were discovered by Weinmann. So coming on to basic composition of composites, it consists of resin matrix, fillers, coupling agents, activator initiator system, inhibitors, optical modifiers or coloring agents. So coming on to resin component, BisGMA resin is a base for composite. In the late 1950s, Bowen mixed bisphenol A and glyceryl methacrylate thinned with TECDMA, triethylene glycol dimethacrylate, to form the first BisGMA resin. Diluents are added to increase flow and handling characteristics or provide cross-linking for improved strength. So common examples include for resin component BisGMA, diluents MMA, BisDMA and UDMA, and cross-link diluents TECDMA and EGDMA. Viscosity of TECDMA is 10 centipoise. So coming on to types of fillers, ground quartz, colloidal silica and glasses of ceramic containing heavy metals are commonly used as fillers. Coupling agent. Coupling agents are used to improve adherence of resin to filler surfaces. Coupling agents chemically coat filler surfaces and increase their strength. Commonly used coupling agents are organosilanes. Silanes have disadvantages. They age quickly in a bottle and become ineffective. Silanes are sensitive to water, so the silane filler bond breaks down with moisture. Water absorbed into composites results in hydrolysis of the silane bond and eventual filler loss. Commonly used silane agents are gamma methacryloxypropyl trimethoxysilane. So these are the pictorial representation of basic composition of dental composites. Here we have resin matrices, coupling agents and inorganic fillers. So coming on to activator initiator system, so based on type of composite it varies. So in case of chemically cured composites, we have the activator is N,N-dimethyl paratoluene and the initiator is benzoyl peroxide. In case of light cured composite, if it is UV light cured composites, activator is tertiary amine and initiator is benzene methyl ether. And in case of visible light composites, we have activator is dimethyl amino ethyl methacrylate and initiator as the activator and initiator is campheroquinone. So coming on to inhibitors and optical modifiers, they are being added to prevent spontaneous polymerization of monomers by inhibiting the free radicals. So butylated hydroxytoluene 0.01% is added as inhibitor in composite resins. Metal oxides in minute amount produce different shades to composites, so in which aluminum oxide and titanium dioxide is commonly added to produce opacity to composites. Coming on to classification of composites, based on the mean particle size of the major fillers, we have traditional composites, small particle composites, microfill composites and hybrid composites. Traditional composites have the mean particle size of fillers of between 8 to 12 microns and small particle composites 1 to 5 micrometer and microfill composites 0.04 to 0.4 micrometers and hybrid composites 0.6 to 1 micrometers. So based on filler particle size and distribution, we have macro fillers, midi fillers, mini fillers, micro fillers and nano fillers. So macro fillers between 10 to 100 microns, midi fillers between 1 to 10 microns and mini fillers between 0.1 to 1 microns and micro fillers between 0.01 to 0.1 micrometer and nano fillers between 0.005 to 0.01 micrometers. So now classification of composite fillers. So classification by filler particle given by different authors. Classification by filler particle size. We have O'Brien's classification given in 2002, Lutz and Phillips classification in 1983, and Lehn-Filters and Lemon's classification given in 1988, and Phillips classification given in 1991, and Crispin's classification given in 1994. So coming on to class of composites, the particle size and the clinical use of it in places. So traditional composites of large particle size with a particle size of 1 to 50 micrometers is being used in high stress areas, and hybrid composites of large particle size with a particle size of 1 to 20 micrometers and 0.04 micrometer silica. It's used in high stress areas requiring improved polishability in class 1, 2, 3 and 4, and hybrid composites with midi fillers with zero point 0.1 to 10 micrometers of glass and 0.04 micrometers of silica can be used in high stress areas requiring improved polishability and in class 3 and 4, and hybrid composites with mini fillers or SPF has been with zero point 0.1 to 2 micrometers of glass and 0.04 micrometers of silica can be used in moderate stress areas requiring optimal polishability and class 3 and 4, and packable hybrid composites with midi or mini filler hybrid but with low fillers can be used in situations where improved condensability is needed in case of class 1 and 2, and flowable hybrid composites midi filler hybrids but with finer particle size can be used in situations where improved flow is needed in case of class 2, and homogeneous microfill composites with a silica particle size of 0.04 microns in low stress and subgingival areas that require high polish and luxure, and heterogeneous microfill composites with 0.04 micrometer of silica and pre-polymerized resin containing 0.04 micrometers of silica in low stress and subgingival areas where reduced shrinkage is essential. So coming on to curing lights, we have LED lamps, QTH quartz tungsten halogen lamps, PAC plasma arc curing lamps, and argon laser lamps. So LED lamps using a solid state electronic process, these light sources emit radiation only in the blue part of the visible spectrum between 440 and 480 nanometers, and QTH lamps have a quartz bulb and with a tungsten filament that irradiates both LTV and white light that must be filtered to remove heat and all wavelengths except those in the violet blue range, and has a wavelength between 400 to 500 nanometers, and plasma arc lamps uses xenon gas that is ionized to produce a plasma. The high intensity white light is filtered to remove heat and to allow blue light between 400 to 500 nanometers to be emitted, and the argon laser lamps have the highest intensity and emit at a single wavelength. Lamps currently available emit 490 nanometers. So coming on to degree of conversion is a measure of percentage of carbon-carbon double bond that have been converted to single bond to form polymeric resin. The higher the degree of conversion, the better the strength and wear resistance. Conversion values of 50 to 70% are achieved at room temperature for both types of curing system. So coming on to C factor, it is a cavity configuration factor. It is the ratio of bonded to unbonded surfaces of the dental cavity, and its value is supposed to be directly related to the stress developed at the interface bonding area. This concept was given by Filzer. It's very important in adhesive dentistry because it is related to the incidence of polymerization shrinkage in composites during light curing when the composite pulls away from the bonded surface towards the direction of curing light. So polymerization shrinkage is a problem because it leads to post-operation sensitivity, bond failure and secondary caries. So here we have the C factor for different cavities. For class 1 it is 5 by 1 which is equal to 5, so it has the highest C factor. And for class 2 we have 4 bonded surfaces to 2 unbonded surface, so the C factor is going to be 4 by 2 which is 2. And in case of class 3 we have 3 bonded to 3 unbonded surfaces, so it's going to be 3 by 3 which is equal to 1. In case of class 4 we have only 2 bonded and the other 4 are unbonded surfaces, so it's going to be 2 by 4 which is equal to 0.5. In case of class 5 we have only 1 bonded surface, so it's going to be 1 by 5 which is equal to 0.2. So it has the class 5 has the least C factor. About the various ways to reduce C factor, so incremental buildup and cavity configuration. One technique is the attempt to reduce the so-called C factor configuration factor, which is related to the cavity preparation geometry. A layering technique in which restoration is built up in increments reduces polymerization stress by minimizing the C factor. Incremental technique overcomes both limited depth of cure and residual stress concentration. So polymerization shrinkage, generally polymer engages less volume than the monomers, the difference of which is termed as polymerization shrinkage. During polymerization, the weak van der Waals forces between the monomer chains are converted to covalent bonds, thereby decreasing the distance between them. The monomer molecules, which are held together by van der Waals forces with the intermolecular distance of 0.3 nanometers to 0.4 nanometers, are replaced by covalent bonds after their polymerization, where the intermolecular distance is reduced to 0.15 nanometers. This reduction in the distance between the molecule leads to volumetric polymerization shrinkage. So in this slide, we can see the effects of polymerization shrinkage in simple. Here we have the microleakage, debonding, fracture of materials or cusp, and the Renton hypersensitivity. So coming on to factors affecting polymerization shrinkage, so we have seen about the C factor. So class 1 and class 5 exhibit greater stress because the restoration is bonded to 5 walls of the cavity. High C factor results in debonding of the restoration. Lower stress is seen in the class 4 cavity because it has enough unbonded surfaces providing stress relief. Hence, it is important to have lower configuration cavity. So in case of class 5, we have two different forms. So in which one form has the lowest configuration factor and the other one has the highest configuration factor. Now we have composition of resin composites. A resin matrix with monomers of high molecular weight will result in lower shrinkage values than those formulated with monomers of lower molecular weight. So molecular functionalities, molecular structure, mass and size have major influences upon the amount of shrinkage and also on monomer viscosity. Coming on to material properties, there are three inherent properties of the resin composites that are crucial over the magnitude of stress, which is volumetric shrinkage, material stiffness, and degree of conversion from double bonds to single bonds. So coming on to filler volume fraction. Filler volume fraction is inversely proportional to volumetric shrinkage. As the volume of filler content increases, the volume of resin matrix decreases, and hence volumetric shrinkage reduces proportionately. So coming on to intensity of curing light, higher the light intensity, greater the polymerization shrinkage. This is due to the greater degree of conversion. The slower polymerization retards the gel point, which provides time for stress relaxation. So methods to minimize polymerization shrinkage. So modification in the photoinitiator is camphoquinone being substituted by phenylpropanedione reduces the stress produced by polymerization. So coming on to soft start polymerization, in this technique, curing begins with low intensity and ends with high intensity. This offers advantage of stress relaxation before maximum possible conversion. So soft start polymerization is subdivided into three techniques. We have stage cure, ramped cure, and pulse delay. So stage cured or delayed curing, the restoration is initially cured at low intensity until the contour and shape of the restoration is achieved. A second exposure with high intensity is applied to cure the final restoration. This provides substantial stress relaxation period. Coming on to ramped curing, the intensity is gradually increased during the polymerization process. It is achieved by increasing the intensity with every 30 seconds, either by bringing the light closer to the tooth or using a curing light designed to change its intensity. This allows the light curing material to have a prolonged gel phase during which the polymerization stresses are distributed readily. So coming on to pulse delay, curing done for 10 seconds at 1 centimeter distance with a time gap of 10 seconds followed by 20 seconds curing in contact with the tooth surface proves to be a suitable technique to reduce the polymerization shrinkage without compromising the degree of conversion. Thank you.